The other algorithm we'll look at is insertion sort, whereas selection sort is really just an academic curiosity. It's something that it's nice to know, but it's useless in practice. Insertion sort is a real practical algorithm, and it's used all the time. Let's look at it. We've got the cards here, and what we're going to do is start with I as a sorted list. So note that when I look at just one element I can just say, well, that's sorted because there's just one, it's sorted. What I'm going to do now is look into the array and just pick one more card. So I'm just going to go one. I'm not going to look at all of them. I'm not going to go find them in. We know that takes linear time. So what I'm going to do here is just look at one card and see if that card is in order or not. In this case, it is, so I'm done. Now I've got two cards in order. So I'll do this again. I'll just increment my counter I by 1, and I'll look to see if this card is in order. And now you can see this is not in order, and that's the purpose of the second index variable here, j. What j is going to do is go down through these guys in order to determine whether or not the ith card is in order or not. So in this case, we can compare j and j minus 1. We'll see they're not in order, so we need to swap. And now we can compare j and j minus 1 again, not in order, need to swap. Then we've got everything set. We can increment I by looking at one more element. And we just repeat this process. So we just have to get it in the right place and move forward. So note again, we have a doubly nested loop. I is going up by 1 every time. But now the inner loop is data dependent. It doesn't necessarily go all the way every time. See, we just went once. We may be unlucky and have to go kind of far, but we can also get really unlucky and have to go all the way to the end. Yeah, sad. But we can also get lucky. Look, 9, it's not that far off. We're just going to do one little swap. So if things are more or less already in order, we're not going to do that many swaps. You can imagine what the worst case is here. What's the worst case going to be? Oh, it's going to be if it's backwards. So if it's reverse sorted, I'm going to get in trouble. But that's how the algorithm works. It does work. What's the invariant we're maintaining? Well, in this case, very different from selection sort. We're not necessarily putting things in their final places immediately. What we're doing is just looking at one element, moving it to a place that's in the right order for the elements that we've seen. We may move it again based on something we see in the future, like if we see 1, we may have to move the 3 that we just shoved in here. But that's okay. We will eventually end up with everything in order. And the important thing here is that we haven't even looked at all of these elements, though. So we're only looking from 0 up to I. We never look at anything beyond I. Implementing this algorithm is not difficult. To move the pointer again, we can simply increment I. And as we do that, we need to, of course, check the newest element and move it into its place. And again, we do that with a loop. So we have an inner loop here. In this case, we're starting with j equal to I and going down to 0. There's actually two ways to get out of this loop. So one way is that we'll just hit 0. The other way is that this conditional, the if, will go false. And if the conditional goes false, we will break out of the loop. So the break statement in Java, like many languages, leaves the innermost loop that we're executing. And so here, when we get two things that are out of order, we'll swap them. And then we'll decrement j to continue down. So we just keep moving j down until we either hit 0 or we don't have to move it anymore. So let's run this code on the same inputs we had before. So we'll have a random array of unique elements. I'll have a random array with only 2 elements, so that's 0 and 1. And I'll have a random array that's partially sorted. So this is an almost sorted array. And we can look to see what kind of operations we're getting. For completely random data, this algorithm is performing about the same as selection sort. For only 2 values, we're getting about half the cost. We get a big win though for partially sorted data. And that makes sense. For partially sorted data, we're doing much less work to actually just swap those things into their place. So big win there. If we run this a couple of times, we'll get different numbers, but not dramatically so. It might be interesting to try this with a different number of unique elements. So here I've got 2 unique elements. What if I have 4 unique elements? How is it going to change this second test? So let's try it out. You can see that with 4 unique elements, I'm actually doing a little bit more work. And if I go up to 8 unique elements, presumably it'll even be more. Let's try. Indeed, it's true. So it doesn't seem like you need that many unique elements to actually be getting performance pretty much the same as having them all unique. It may be helpful to visualize that. Let's look and see what happens for these 4 cases. So random, nearly sorted, reversed, and few unique. So if we look at the few unique, you can see it's, we're doing a little bit better than random and reversed, but not hugely. Look how fast nearly sorted is though. Zoom. Then we have random and few unique, random, and reversed. So these kind of visualized results are corresponding to what we are getting in the experiments. How do you analyze this algorithm? Well, what's the worst case? It looks like it is reversed, and that makes sense because what I'm doing here is putting something in its place that is completely the wrong place. So I've got to always move it over whenever I get a new element. And I've got to move things all the way down. So what's happening here is the first time around, I'll just do 1 swap, then I'll do 2, then I'll do 3, then I'll do 4, then I'll do 5, then I'll do 6. So here, the number of comparisons and the number of swaps are going to be roughly equal. If I just look at the swaps or exchanges, I get numbers like this. So for 32,000, I'm doing about 255 million swaps. Let's instead count the comparisons and ignore the swaps, and you'll see that the numbers come out roughly the same. So for 32,000, again, 255. And this makes sense. Let's just think about what the best case is for insertion sort. Well, the best case is that this less operator always returns false, so we immediately break out of the inner loop. That would mean that the inner loop is only executed once. We're only checking 1 comparison. And therefore, the total complexity of this is linear. I go from I is 0 to n, and then execute the body of the loop exactly once. That's the best case, and that corresponds to the case where the array is already sorted. What am I doing in this case? Well, what I'm doing is just looking at each element and comparing to the previous one. I see that they're in the correct order, and so I just move on. This corresponds to the code that we had for checking whether or not an array was sorted. What does that algorithm do? Well, it goes through the array once, comparing adjacent elements. If it finds 2 that are out of order, we return false. Otherwise, if we drop to the end and we didn't find anything out of order, we return true. This is exactly what insertion sort does in the best case, where no swaps are necessary. What does insertion sort sound like? Let's find out. Yeah, but can you dance to it? Just to remind you what selection sort sounded like. It's not fair because this is a much smaller array. So how big was that array? Anyway, it's definitely not as big as this one. So that's the sound of insertion sort. But in fairness, note that this is a much bigger array. So it did take a little longer, but that's because there's just more elements. It's fun to listen to more sorting algorithms. We're not going to actually talk about many more in this class. I'm going to present one more, which is called heap sort. Let's see if we can hear what it sounds like. Oh, this is quick sort. Whoa, quick sort, merge sort. It sounds to me like a Pac-Man game. It's done. Yay. This is heap sort, which we will talk about in a later lecture. You can see this is a two-phase algorithm. The first phase did a little funny pass, and then the second phase is doing this thing. Note it goes backwards. Heap sort. That's radix sort that you'll see next quarter. This is the recursive radix sort. This is a practical sorting algorithm. This is GCC, which you can see is a hybrid algorithm. It does a little quick sorting and then a little insertion sorting. Here's the insertion sort pass. So essentially we're doing quick sort down to a certain level and then just insertion sort to clean up the last little bit. More importantly, what's the Romanian folk dance for insertion sort? And here you can see 0 and 1 are having a little interchange there. And now 0's in his happy place. And so 3 and 1 have to compare each other. And you'll see they're going to swap. So 3 now is going to compare. Oh, they're happy. They're done. So now 3 and 8 are going to compare to each other. And they see that they're in the right order, so they're done. Now 7 and 8 go on and on. This goes on for 3 minutes, and you can watch it all on YouTube.